In this video, we discuss the generator out-of-step condition and introduce Beckwith M3425A, Advanced Generator Protection Relay. Any synchronous machine connected to network can be modeled as this picture. The protective relay, which is an impedance sensing element, is assumed to be located at the sender terminals, with terminal voltage Vs and the current of Is. Current flows from S towards R. The relay measures the impedance of Z. The relay at sender terminal will measure the value of the impedance represented by AO. If a severe disturbance occurs, then the load angle delta S increases and the impedance measured by the relay will decrease to the value AQ, which can be inside the relay operating characteristic. The locus of the impedance seen by the relay during oscillations is a straight line when ES equals ER, as shown in this picture. If ES is not equal to ER, the locus is a family of circles centered on the SR axis. Any changes in load or machine's condition move this impedance to left or right. The impedance move has a transient period till it reaches to new steady state condition. If this transient change end to new steady state condition, a power swing has happened, and the system continues to work. However, there might be a condition that this transient period doesn't end in steady state condition. In this case, pole slip or out-of-step condition happens. During pole slip, machines experiencing very high current, usually higher than 3-phase voltage short-circuit current, which is dangerous for machines and system. Generally, out-of-step condition has to be detected fast, and the out-of-step machine has to be isolated from the system. In some condition, machines might gain synchronous after few cycle of slipping. In this case, pole slip counter counts how many times the poles crossed each other. The point where the impedance locus intersects the total impedance line between S and R is called the electrical center of the system. At this point, the two machines are 180 degrees out of phase with each other. As the locus keeps moving to the left, the angular separation increases beyond 180 degrees, after that the two systems move into phase again. Once the two generators are back in phase again with each other, we can say that the generators have completed one slip cycle. Measuring variations in system impedance helps to detect an out-of-step condition and define the schemes for out-of-step protection. Settings applied to these schemes are critical to system reliability and stability. The schemes must be set to quickly isolate a machine, not only to prevent damage, but also to prevent instability from spreading to other portions of the system. For fast out-of-step detection, a MOHO element will pick up, as the impedance trajectory follow the path as shown in this picture. As the swing proceeds and crosses blinder B at Z1 at T1, blinder B will pick up. When the swing reaches Z2 at T2, blinder A will drop out, and if the speed of change of impedance is faster than setting, a trip will be generated. In some case, a complete swing needs to be detected to trip being generated. In this case, for the trip to occur, the swing must progress and cross the MO circle at Z3 where the MOHO element drops out. The benefit in setting to trip the breaker upon exiting the MO characteristic is to allow the circuit breaker to open when the angle between the generator and system voltages is 90 degrees or less, a more favorable angle with higher impedance for arc interruption where the current flow at trip is reduced. To set the relay, we need to know electrical center of the system, Generator's transient impedance, step-up transformer impedance, and system impedance are required to calculate the electrical center of the system. Here is typical setting. Here is an example system. A cogen plant with a double line connected to the grid. A fault happens at line B, close to plant's substation. The fault clear in less than 200 milliseconds. During the fault, generator current and rotor angle increases. Impedance relay will follow the impedance trajectory. As we see, the impedance entered to MOHO zone but came out from the same side. If the fault clear after 400 milliseconds, the generator rotor angle will increase to more than 120 degrees. The generator cannot recover from this situation and enter into pole slip condition. Here is impedance trajectory in this condition. As we see, the impedance enter MOHO zone and exit from another side. In this example we see why using a simple overcurrent for line protection might not be a good idea, as within 400 milliseconds we are not dealing with only a fault on the line but an out-of-step generator as well. Beckwith M3425A is an advanced generator protection relay. Beckwith M3425A provides voltage-based, current-based, and impedance-based generator protections. Here is an overall functionality of Beckwith 3425A. Out of step. Split phase differential. Stator differential. Under frequency time accumulation. Inadvertent energizing. Turn-to-turn fault. Load encroachment blinders and power swing blocking for system backup protection, to enhance security during abnormal system conditions. Excitation ground protection. 100% stator ground fault protection by low frequency injection.